Hello everyone, I am Muhammad Asif Hussain, first author of the paper Domain Adaptation in Crowd Counting, and now I am going to present it. So my corresponding authors are Mahesh Kumar Krishna Reddy, Kevin Cannons, Janju, and Yang Wang. So the main goal of this project is to optimize the parameter of a pre-trained crowd counting network, which means we are going to train our network in source domain dataset, like which is having a lot of images from maybe one domain or maybe from different domain, and then we are going to optimize the parameter on a new target domain by considering three different settings, so SDA, SSDA, and UDA. And this parameter optimization is basically done by domain adaptation technique. Now we are going to see what is crowd counting. The task of crowd counting is defined as approximating the number of people that are visible within a given image. An effective crowd counting system can accurately estimate the size of the crowd regardless of the crowd density, background environment, viewpoint, illumination, etc. If we see the examples here, on the leftmost column, the bottom image, so the difference with this one, with the rightmost bottom one, is like density variation. So the left one is more dense and the right one is like sparse. So we are kind of trying to train our network uh, on say high dense, and we are going to test it on low dense or sparse images. So this is how actually we are going to perform domain adaptation on crowd counting. Actually, in crowd counting, domain means basically the different density variations among the images. Also, it could be image environment and background. It could be crowd appearance or illumination, or maybe camera perspective. But in this paper, we basically focused on like density variation and image environment or background. So we consider this as the domain to be adapted in new target domain. So the source domain basically means we train our network in one data set, which might contain images from different cameras or maybe from one scene. And the target domain, which is completely different from the source domain, the distribution is different. So our goal is to adapt to this new target domain data. So the objective of domain adaptation here is to train the network on source domain data and inference on target domain by adapting to the target features. As shown in this figure, source domain images correspond to features that form a cluster in latent space as indicated by the blue circles. Target domain samples produce a similar cluster in latent space as shown by the orange diamonds, but these clusters are separated. This is called the domain gap. By domain adaptation, our focus is to minimize this gap and making the clusters more overlapped. So the potential application includes leveraging the lack of level data, as we are considering semi-supervised and unsupervised domain adaptation. So in some cases, we don't need level data. And also the problem setting is like close to real world deployment of crowd counting system. And the scenarios we considered are like semi-supervised setting, where we used a few labeled examples like 1, 5, 10, and lots of like unlabeled examples during training. For supervised setting, again, we used a few level examples, but in unsupervised setting, we didn't use any level examples to train our network. So this is our network architecture. So we have two streams in our network architecture, that's source stream and target stream. So in the middle, we have the feature extractor. This is nothing but MCNN.
multi-column architecture. So we can call it the backbone network. Anyways, the final output of these two networks are basically the density maps after applying one by one conv. Then we are trying to calculate the MMD between these two. This is how we are minimizing the domain gap between these two density maps. So to fine tune the network, we basically used three loss functions. One is for source stream, which is simple MSC loss, and for target stream uh, with the label data sets, like for uh, semi-supervised example and supervised examples, we again use like MSC. But for unsupervised domain adaptation, as we don't have label, so we used MMD loss with a variable alpha. We already know about MMD. So the main purpose of using MMD is to reduce the gap between the source domain and target domain. So we basically use the same concept here. We try to translate our target domain features to source domain feature, and we already train our network in source domain dataset. It already performs better. So after translations, it would be easy for network to perform counting. So that was our main intuition. Here, MMD works as unsupervised regularizer, and also it uses to measure the similarity between two feature representations. So we perform testing on four data sets: Shanghai Tech A, Mall, UCSD, and Trancos. Here, Shanghai Tech A, Mall, and UCSD are human-centric dataset, and Trancos is vehicle-centric. We also use MA and MSC as the evaluation metrics to measure the performance of our network. Basically, these are the quantitative results for our algorithm tested on four datasets. On the left table, this is SSD and SSDA, and on the right table, this is the results of UDA. Here, source to target we means train on source dataset and domain adaptation on target dataset. So we have two baselines here. First one is like in model column. You can see the first one is pre-train and the other one is like fine tuning. So red is the best model with less MAMSC and the blue one is second best. So we can see that our model is outperforming over SDA, SSDA and UDA in all the algorithms on different data sets. So let's have a look at our qualitative results. Here the first row represents the input images and the second row represents corresponding output density maps. So the first column here the network is trained on UCSD dataset and tested on Trancos. The second column network is trained on Mall, tested on Trancos. The third one network trained on Mall, tested on UCSD, and the fourth column network trained on UCSD and tested on Mall. So overall the results are quite accurate and consistent, with our system correctly identifying most of the people and vehicle in the images. However, I would like to point out one interesting failure case in the bottom row of our second column. Here you can see that the bus was actually missed, which was likely due to the fact that buses appear very infrequently in the data compared to other type of vehicles. These are the results for cross-domain adaptation. Here, basically, we train our network on human-centric dataset and we test it on vehicle-centric dataset. Like UCSD to Trancos, in the first row of the table, it means the network is trained on UCSD dataset and it was tested on Trancos dataset. And also we can see that for cross-domain adaptation, the results are pretty consistent to the previous tables. So these are the main contribution for this work. First of all, I would like to say like we propose a new task definition that is closer to real world application. And secondly, our method is simple and efficient for adaptation with a few parameter updates. Also proposed method outperforms other baseline like we saw from like previous tables. And we did strong emulation study to support this proposed solution. These are the references I used in my previous slides. So thank you everyone for listening to my presentation. You are welcome to see our poster and stay safe. Good luck.